Recently, I got myself a M5 PaperS3. It's an ESP32 S3 dev kit shaped like a pocketable e-reader, featuring a 4.7-inch 960 by 550 Eink touchscreen. What makes it special compared to other small Eink dev kits is that it has got a screen with a raw roll column driver interface, also commonly referred as parallel interface, but that's a different parallel interface compared to LCD. This enabled me to drive this screen while bypassing the normal waveform method. This would in turn make a high refresh rate possible, up to 60 to 70 FPS. More on that later. That got me thinking, what kind of fun stuff I can do with it other than writing an e-reader application. Several years ago, I made a GameBoy FPGA reimplementation, so it's fair to say I have at least some understanding of the GameBoy architecture. How about combining both? I searched online and found no one have ever attempted building a such thing. As a result, I'm really tempted to create the first Game Boy emulator for the PaperS3 and make it actually playable. The first thing I started working on is the high refresh rate Eink driver, because this is the component that decides if this project would ever work or not. Eink are generally perceived as slow, low refresh rate and slow response. However, it's possible to improve it drastically given the hardware. I have a dedicated video about how to do 60 Hz and low latency on Eink and how I turn it into an Eink monitor. You can view it here. But basically, if you treat each pixel individually, doing pipeline updates, and pay the cost to use an FPGA to run all these, you can get really smooth image on Eink. Now, I just need to see if I can do the same on the ESP32. Luckily for this project, I don't really need to process all the pixels on the screen. Game Boy only has 160 by 144 pixels. I need 3 pixels to represent 4 shades of gray. Duplicating desired image by 3 times, I get 3x pixel perfect scaling and desired image. This means I only need to process 160 by 3 by 144 pixels at 60 Hz, a much lower target than 960 by 540 at 60 Hz. I'm storing 4 bits of states per pixel. It gets compared with the incoming buffer to decide what to send to the screen. The LCDIF and DMA is used to actually pumping out the pixels to the screen, so the core can calculate next batch of pixels to display. The whole thing runs on the second core on the ESP32. Each iteration is set to run for around 17 milliseconds, providing a 60 Hz refresh rate. Double buffering is also implemented, allowing the emulator to render tear-free image. While I have implemented a Game Boy emulator in the past, that was also on FPGA. Game Boy emulator on microcontroller has been done many times over. So I decided to use existing emulator instead of reinventing the wheel myself. I tried 3 existing emulators as the core: the Peanut GB, the Walnut CGB, and Crankboy. Peanut GB seems to be most popular emulator option, with decent performance on microcontrollers. Walnut CGB is a fork of the Peanut GB. It modified the emulator to do 16-bit instruction fetch instead of 8-bit fetch, potentially saving the time on memory access, mostly saving time on the expensive emulated memory mapping path by issuing less memory access. Crankboy is a fork of the Peanut GB and a front end for the Playdate project, offering a complete optimized Game Boy emulator for the Playdate. They added many optimizations for the port, especially also around the memory mapping path, allowing much better performance without the rather unusual dual fetch architecture from the Walnut CGB. I tried them out on the ESP32 S3. I tested the emulation speed in various titles, and here are the results. Performance are measured as relative to Game Boy, one meaning it's running at roughly the same speed as the Game Boy. I used the most performant Crankboy as the emulation core. With dynamic framescape, it can hit 100% speed in many titles, rendering at 30 to 60 FPS. The actual frame rate depends a lot on the runtime situations. With the current performance, it's rather unrealistic to enable Game Boy Color support for now though, as the Game Boy Color would allow the CPU to run at double speed. We are not even close. All three emulators uses Mini GB APU as a sound emulation engine. The Game Boy integrates a 4-channel programmable sound generator, 2 channels of square wave, 1 channel of sample, 1 channel of noise. 4 channels are then mixed together to produce the sound output. In a real Game Boy, some part of the mixing happens in the analog domain, but generally for emulators, it's easiest to just do everything as PCM samples at 32.768 kHz sample rate. All modern sound cards play back PCM samples anyways. This is however not the case on the PaperS3. The PaperS3 only has a buzzer, capable of generating a single tone when driven by the PWM. One well-known technique is to use a PWM DAC to output PCM samples. Basically just send DC bias PCM samples right into the PWM module as a duty cycle. However, on ESP32S3, PWM module couldn't be fed by the DMA. It needs to be either pulled or generating an interrupt at a sample rate to update the duty cycle register. Both would require me to reserve some CPU cycles just for outputting the sound. Instead, I used the PDM output capability of the I2S peripheral. It was intended for connecting to DAC or amplifiers accepting PDM, but you could also just add a RC filter to it and itself becomes a DAC. I implemented this first, and it worked right away. But the issue is, it's just way too quiet. I thought it might be because the modulation frequency was too high, so I also tried just 32 kHz PWM, but it doesn't make any meaningful difference, so I'm sticking with the PDM. But I felt like that was not enough. Yes, it does have sound, but if it's not audible in many situations, it's not that useful. To make loud enough buzz, it pretty much has to be a single tone, something it was actually designed to do. So how about actually just using a single tone? You see, on Game Boy sound generator, first 2 channels are straight square wave. The sample channel could often be approximated with a square wave. While being a bit far-fetched, I could use square wave in place of noise. Then it's just 4 channels of square waves. While the buzzer can only do 1 tone, it's possible to switch between multiple sound channels rapidly to create a pseudo-polyphony effect. This is a well-known technique on platforms also only has a single buzzer, such as an IBM-compatible PC without any sound card. Regarding the results, I think it works surprisingly well and bad at the same time. The good part? It's loud and clear. Game music are still very recognizable, and it's overall interesting to listen to. The bad part? Well, the Game Boy is never supposed to sound like that. To ensure all these don't eat into the limited CPU resources for the emulation, I put the entire PSG emulation on the second core. Based on the profiling on selected games, sound emulation generally runs for up to 2 milliseconds per frame, depending on the sound complexity. The input is rather straightforward. The M5 PaperS3 has a touchscreen, so it's natural to just show a touchscreen joypad on the screen. For serious gamers, though really, I have also added experimental Bluetooth LE joypad support. Though it doesn't actually fully implement the HID protocol, it only guesses about the report format. As a result, the compatibility is quite poor. I think as a demo this is fine, but this definitely can see some improvements. I added another feature, quick save and quick load. This basically stores and loads the state of the entire emulated Game Boy, allowing quickly creating checkpoints and return to the checkpoint. So the idea is, when the next time you pick up the PaperS3 after you shut it down and put it away, you can just quick load to get back to the game immediately. In conclusion, I think the end result is a pretty decent or usable Game Boy emulator for the M5 PaperS3. It's sad that PaperS3 has already reached end of life. Hopefully, we get a proper replacement for it soon. If you want to try this firmware out, it's available on the M5 burner. Thank you for watching, and I will see you next time.